My name is Professor Mark Wallace. We've developed an AI-based technology for fleet scheduling that is now deployed in Opturion's Dynamic Transport Optimiser. The challenges in transport fleet optimization are to deliver all the orders that have been placed, to schedule slots and bays for their pickup and delivery, to minimize the cost of the fleet and the cost of drivers, but to maintain driver safety in terms of alertness and driver satisfaction. The problem in delivering all the orders is because orders are complex. Some orders are placed in advance, the day before the day of operation. Some days are placed on the day of operation. The requirements for each order have a pickup location and delivery location. They may have a weight and a volume, which impacts the kind of vehicle that can carry them. They'll have a delivery time window, the earliest delivery and the latest delivery, and possible service time, so the time to load or unload a vehicle. There are additional constraints on the locations, their opening times, constraints between locations and vehicles, so which vehicles can go to which locations. There are compatibility constraints, so frozen goods can't be transported on a vehicle which doesn't have any freezing facility. And even order-order compatibility. So, for example, for prisoner transport, you can't transport in the same load certain different types of prisoner. Just looking at the allocation of vehicles to orders, we have a capacity constraint. So a small van, say, can only have a capacity of 10. If we have orders A and B, and their weights are 5 and 3, they can fit in van 1. And we can actually allocate a set of orders to a set of vehicles based on their capacity quite successfully. However, what happens if additionally we have deadlines or time windows? So orders F and G have almost the same time window. That means they can't be delivered by truck 2 at the same time. So we have to actually change the vehicle assigned to order G so it can be on a different truck. So one thing is to deliver all the orders. Another thing is to actually minimize the costs of the fleet and the drivers and to maximize the convenience for the customer. So we have a set of objectives which we're trying to satisfy. One objective is to minimize the total travel distance, which is essentially minimizing the total travel costs. So supposing orders A and B are assigned to van 1, well, if their locations are very far apart, then van 1 is forced to travel a very long way in order to deliver just 2 orders, while van 2 may be just delivering to L4, one location. So we simply swap orders B and D between the vehicles, and now that van 1 has a much shorter route, and van 2 can pick up the route to L2. Another cost is the cost of a driver working all the day, and so sometimes we want to minimize the number of drivers by packing as many orders as possible onto a single vehicle. And there's also a cost sometimes for actually using a vehicle as opposed to not using it. But again, if we have time windows, this might mean that all those things can't be done by the same truck within a certain time window. We have to distribute things across multiple vehicles again. So we have to balance the net cost of drivers against the possible delivery. When we take into account the locations, we take into account the cost of drivers and vehicles, we take into account time windows, even a small problem with just 10 orders like this becomes very hard to solve mentally by one person on a spreadsheet. However, there are still further constraints and requirements, and this is about the driver, by ensuring that drivers can stick to their shifts, that they have breaks during their shifts, that they end up at the end of a shift somewhere near home, so they're not driving a huge long way at the end of the shift. We want to actually ensure that contractors have a minimum workload so that they don't leave and not offer their services to the company anymore. And often we sometimes want to make sure that drivers have an area of work where they deal with familiar customers. Just thinking of driver breaks, we can vary the duration of a shift, so we might have a 10-hour shift, and then we have different possible break lengths, and that might affect the maximum time required between the breaks. Also, we've got to take into account break locations, whether they have to be at the depot or at any cafe en route, or whether it can even be done at the side of the road, like this picture here. Or they might be done while the vehicle is loading. When we say dynamic transport optimizer, there is one other feature, and that is how to handle new orders on the day of operation, or any other changes on that day. In the case of a new order, we've got to consider where the pickup location is. Is it at the DC? In which case we just have to consider the trucks that haven't left the DC yet. Or is it elsewhere? How large is the order? What trucks will it fit on? Where is it at a location? So which trucks are going near there? And what's the deadline? Are they going near there at the right time? So we need to reschedule. We need to choose a truck to handle this order. We need to ensure that all the other deadlines in this truck can be met, or else other orders for that truck can be transferred to other trucks. But we still need to minimize changes to the whole schedule. We want to work out the risk or the cost of missing time windows because we've got a tighter schedule now. And we've also got to make sure that drivers don't end up with a large amount of overtime or getting exhausted working beyond the end of their shifts. Here is a short demo of Dynamic Transport Optimiser. We have a set of locations, and each location has an address and time windows and deliveries that can be done there. These locations are all in red because none of them have been visited yet in any plan. We have a bunch of constraints which can be edited online to actually set up the problem. We have the input in terms of all the different locations and their coordinates, the orders and the fleet. Given any piece of input, so for example selecting a vehicle, we can edit that input, updating any of the properties. So for a particular vehicle, we can edit the costs over time, times, penalties, and so on. We can also edit the driver brakes for the driver of that vehicle. Once the data is set up, we can press solve, and the system starts to create solutions. It creates them quite quickly and creates better and better solutions. At any point, we can check the warnings that have come out of the system, and then we continue with the search. And we can stop the search at any point, and we have a solution. It may not be optimal, but it's a good solution. And we can look at the actual sequence of activities carried out by each vehicle in the solution. We can also look at the vehicles online on the map, so we can see actually the route that they've carried out and what they're doing at each location when they arrive there and so on. We can also look at the unassigned orders. So for example, we can see that there are 2 unassigned orders, and we can have a look at the reasons that they're unassigned as far as the system can diagnose. So in the first case, we've got an order weight of 1600, which is much greater than the maximum capacity of any vehicle in the fleet. Clearly this weight is just an error of the input, so we correct the input, and then we can continue with the search. In conclusion, a fleet scheduling solution has to be designed to meet all the complex constraints on orders, trucks and drivers, to optimize the schedule so as to maximize customer satisfaction, to keep the drivers safe and happy to work for the company, but also to minimize the bottom line cost of the whole solution. And it must also be flexible in order to be fast rescheduled on the event that new orders appear or there are delays or other events. Opturion has combined all these 3 functionalities in the Dynamic Transport Optimiser.